Good morning, everybody. My name is Martin Crew from Yugabyte. I want to welcome you to our top 5 considerations for running stateful applications on Kubernetes. The discussion this morning is going to be led by our CTO, Karthik Ranganathan, and we will be starting in 2 minutes. Please stand by. Hello, we'll begin the online talk in 1 minute. While you're waiting, please do take note of the Kubernetes poll. We're very interested to find out where people are in their adoption cycle. So please complete the poll, and we'll be back to start in 1 minute. Thank you. Morning again, everybody. Again, my name is Martin Crew, and we're going to be discussing top 5 considerations for running stateful applications on Kubernetes with the CTO and co-founder of Yugabyte, Karthik, and I'm now going to hand over to him for the presentation. As we go through, please do type questions or anything you have on your mind, and at the end of the formal presentation, we'll answer those questions. Thanks, and enjoy the content.
Thanks, Martin. Hi, everyone. We can just jump right in. I'm Karthik, one of the founders and the CTO at Yugabyte, and we're going to talk about considerations for running stateful apps on Kubernetes. Okay, so roughly on the agenda, we're going to first quickly touch upon why even have a stateful set on Kubernetes, what's the point? And then we're going to look at top 5 considerations when you're trying to run a stateful app on Kubernetes, and there's a variety of things to think about, but here are 5 of them. And we're going to look at a live demo of an app, so an end-to-end app running on top of Yugabyte all inside a Kubernetes ecosystem, and then we'll open it up for questions. But like Martin said, please feel free to type your questions in as we go along. Okay, so quick background, like myself and my other founders Karnan, Mikhail, and a whole bunch of other folks at Yugabyte. We all worked together on the database platforms at Facebook. We worked on HBase and put it into production for a number of use cases at Facebook, all massive use cases like the messaging, the Facebook messages, the inbox, the Facebook messages search, the time series and alerting use case at Facebook, as well as like a machine learning style use case for fraud and spam detection to detect spammy users. And these are the similar type of workloads that we are building Yugabyte for. Okay, so before we jump into stateful sets, like a quick intro of why we built Yugabyte and what it's good at, right? And then that'll help the rest of the presentation flow on how it works with Kubernetes and what are the advantages of running it as a stateful set inside Kubernetes and so on and so forth. So we started out with 3 core features. It has to be a transactional database. It has that in a little more detail. So on the transactional side, we wanted Yugabyte to support both single row and multi-row transactions. So distributed ACID transactions as one of the core building blocks, so that we can support consistent secondary indexes on top that are highly performant as well, and build the database with a document-based core that can be exposed using a variety of languages on top. On the performance side, we wanted it to be a low latency database, so it's got to be really, really fast in returning the data that you put in, but also offer tunability in terms of reads, so you can read from a follower from the nearest data center or the absolute source of truth. And it should also be pretty good at handling high throughput, so batch reads, batch writes, and so on. On the planet scale side, the world has now changed to where there are 50 to 100 data centers available to everybody thanks to the large public clouds. And all of these data centers are different geographic regions. So distributing data globally is becoming extremely important. And that's one of the core things that Yugabyte supports, along with the ability to automatically shard and rebalance data. So you don't really have to worry about how to move your data across machines, across geographies, or across zones. Now, on the deployment side, we wanted Yugabyte to be cloud native. So it runs on bare metal, on VMs, or containers, but it's really built to run well inside containers as well. And it also had to be self-healing and by virtue of its commodity machines and low cost is a failure-prone base. To be resilient to failures is extremely important. Finally, what's a database in 2018 that's not open source? So we're an Apache 2.0 licensed database. You can find us on GitHub. And we're doubly open source in the sense the core database itself is in the open, but we also are extending well-known APIs. So we started off with the Cassandra query language, Redis as a scalable persistent database, and PostgreSQL, which is coming pretty soon. Okay, so let's look real quick at how you would deploy Yugabyte without Kubernetes, right? And then we'll map that into how you would do it with. Let's say you had 3 nodes, node 1, node 2, and node 3. You first deploy the Yugabyte master, which is a coordinator. It's a background metadata service that keeps the shards, so on and so forth, and coordinates cluster-wide operations like creating a table or taking a distributed backup or so on and so forth. The next thing you deploy are the tablet servers. The tablet servers store data in the form of tablets. So your entire table is cut up into small shards or tablets, and they're replicated and distributed across a variety of machines. The tablet servers do the actual I/O, but they heartbeat to the master, and the master controls the placement of data across different zones. Now, each of the tablet servers has a document-based storage engine at its core. It's a heavily customized version of RocksDB, and it's really good for ever-growing data sets that are mission critical. In order to replicate this data across different machines, we use a Raft-based replication in order to ensure single-row ACID consistency. And we have a global transaction manager on top that tracks a whole bunch of things to give you distributed transactions. Okay, so now let's get to why do we need to run stateful sets on Kubernetes, right? What's the advantage? Well, the first thing, and this is one of the reasons, like Kubernetes is pretty attractive for stateless applications today. A lot of people are moving to it to be independent of whether you're on-premise or on the cloud or different public clouds, to be vendor, like to be multi-cloud, right? And so on. So the same unified orchestration, if it extends to the stateful side, makes it that much easier for people to orchestrate and run the system. Now, you can have one of the advantages of Kubernetes is you'll be able to package and run it in a variety of different environments, whether it's your laptop, whether it's for integration testing, stress testing, staging environment, pre-production, production, so on and so forth, in a very declarative manner. You will inherit the same advantage on the stateful side as well. And last but not the least, it is a very fast growing community. For the above mentioned and other reasons, people are very interested in being hybrid, in running on-premise in a cloud-native fashion or multi-cloud, like to take the advantages of multiple clouds. So people want to run stateful sets in Kubernetes. So join the community and help shape the future of how stateful sets gets built in Kubernetes. Okay, so let's look at how we would have started a Yugabyte DB cluster without Kubernetes. Well, the first thing is you start the master and you pass it each other's IP address so that they communicate and form a highly available and consistent Raft consensus group. And you pass it a whole bunch of disks so that it can store its data. And for the tablet servers which do the I/O, you again pass it to Heartbeat and figure out which shards they need to host and so on and so forth. So a couple of things to note here. The first thing is that there is a notion of IDs, like you want to start 3 masters and you want to start 3 tablet servers or 4 or 5, but there's a notion of a number built into the system. The second thing is you need to know the address, the IP address of the different masters or a way to refer to them. Now, in a Kubernetes YAML-like system where the VM or the pod has not yet been created, you don't know the IP address ahead of time because it's usually assigned after the pod is created. So this causes a little bit of a chicken or an egg. So that means you would need to have some form of a stable network ID. The third thing is you need to have a notion of persistent disk. So if the process dies and restarts, it can reattach to the same disk because it's a highly available system. It can tolerate a lot of faults. Now, these are the concepts that form the basis for a stateful application. Now let's look at how this maps to existing controllers, right? So existing controllers in Kubernetes are, like, for example, a replica set, but that uses only ephemeral storage and it has identical pods. So there's no way to reference one pod from another. A deployment is really a collection of these replica sets, and it handles like deployment and like recreating this, redeploying it, rolling upgrades, so on and so forth. So that doesn't help stateful applications either. A third thing is the daemon set, another of these controllers, but that's just to run a single daemon on a node, and it really doesn't cater to stateful applications. And finally, there's the notion of a job, which is ephemeral. It has a start time and an end time, and it generally finishes, and that's not really how you think of a database or a stateful application. So that doesn't really cut it. So none of these existing controllers really work for the stateful side of the world. So that's why, like pretty recently in December 2017, the Stateful Sets Controller API GA, it became stable. And this was built after almost a year and a half of careful, deliberate thought. So it's a pretty powerful and useful API for stateful applications. So what does it support? So firstly, it supports ordered operations with an ordinal index. So you can reference your different nodes inside a service using numbers. So let me talk to master number 0, number 1, number 2, or so on and so forth. And this is really useful when you're trying to start a certain number of nodes in a service, scale up, scale down, do rolling upgrades, terminate, attach to certain guys, so on and so forth. The second thing is it has a stable, unique network ID that stays the same across restarts. So just because your master 1 restarts or your tablet server 5 restarts, it doesn't inherit a new ID. The third thing is it has persistent storage. So in the case of a locally attached disk, if you restart the process, it reattaches to that piece of data that it had written. So its storage is persistent. And if it's a remote persistent disk, even restarts across nodes have affinity to the storage that was attached to it. And finally, it supports the notion of a headless service, because very often you don't know the exact members inside the service and you would want to list them. So just by using a CNAME, you'd be able to list the various IP addresses of the pods running inside that service. And we look at in detail at how this is going to map to a Yugabyte example. Okay, so when we're trying to deploy Yugabyte as a stateful set, we have a number of nodes. Each of them has either a local like disk, or it could be an on-the-fly dynamic remote persistent volume. Now we first deploy the masters across the 3 nodes, and notice that they're called YB master 0, YB master 1, YB master 2, so they're numbered servers across 4 machines, or however many machines we need. Right? So that's T server 0, 1, 2, and 3. Now we create a headless service for the YB masters, so you'll be able to list the master 0, 1, and 2, and another one for the tablet server, so you'll be able to list 0, 1, 2, and 3. And this is extremely useful in discovery. So it's very easy to tell the tablet servers how to discover the masters, and it's easy to tell external clients how to discover the tablet servers themselves in order to interact with the database. So the application clients use the tablet server headless service in order to discover the service. Now let's look at a little bit of the YAML fragments to see how this actually happens in code. So this is the example of the YB master YAML, and you can find this on GitHub. So what is interesting is on the left, if you look at the cluster IP, it says it's none, and that's the way you declare a headless service, because we're not exposing a specific IP, we're just allowing external clients to list members internally to be able to talk to them. The second thing on the top right is the fact that there are 3 replicas. For the YB master, the fact that there are 3 replicas just means that the default replication factor of this cluster or universe is 3. And then there's a whole bunch of ports that the master exposes. So the port 7000 is the master's UI port, and the port 7100 is the RPC port. And they're exposed to everybody accessing it as a service. And finally, there's a number of volume mounts. This is the stable persistent store that we talked about. In this case, it's mapped into the pod as MNT disk 0 and disk 1. All right, so the YB tablet servers YAML looks extremely similar. There's a headless service. The replicas is 3. That means there are 3 tablet servers. In the example we mapped out above, it would be replicas 4 because there were 4 pods. Now, notice that the tablet servers reference the master using the CNAME, which is exposed because of the headless service. So they say, it says the T server master addresses is ybmasters.default.svc cluster.local, right? So what that means is the T servers will be able to go to that CNAME and list out all the masters and do the discovery of the masters by themselves. And the only difference here is that it exposes a different set of ports, including the port 9 port and 6379, which is the Redis port, so external apps and clients can interact with it. Okay, so Yugabyte is not the only application that is stateful. There's a number of examples out there. So a simple example of Postgres with async replication. And you can also look at an example of Elasticsearch, which does search. You'll be able to do searching of all your documents and so on and so forth. So there's a number of examples out there, but they all follow roughly the same principles at the core. Okay, so let's get into some of the concerns when deploying this, right? So the first thing is, how do you ensure performance, right? And that comes up with what type of storage to use. And it's an often asked question, should you use a local instance store or a remote store? And they have different characteristics. So the local store has lower latency and higher throughput because it doesn't have redundancy of data, whereas the remote storage is often has higher latency and lower throughput. Now, local store is really good and recommended for applications like Yugabyte DB, which does its own replication and is highly available, while remote storage is a great option for something like a Postgres, where there is no replication internally, so the data has to be persisted by the remote storage, which does its replication and redundancy. The local storage is usually provisioned outside of Kubernetes because either the machine has a local store or it does not, so it has to be provisioned at the time the machine is created. But fortunately, that's really easy to do in a public cloud environment, while remote storage is dynamically provisioned by Kubernetes in a public cloud. Of course, in a private data center, that has to be pre-provisioned as well. Now, you can use typically, it's recommended to use SSD-based local store for latency-sensitive apps to get really low read latencies. And on the remote store, you can use this alongside an app that does like Yugabyte DB in order to do tiering so that you can keep your costs under control when you have a lot of data. There's a couple of examples. The example below shows, like, I think the most interesting, there's a node selector which has GKE local SSD :true. So you tag your pods with certain labels, and you place your pods on nodes that match those labels. And okay, so the second aspect that's extremely important is how do you ensure data resilience? Because typically in Kubernetes, if you don't specify like the number, and you typically don't want to specify the number of CPUs because you want the pods to expand and use as many CPUs as they need, you have the risk of having multiple pods being scheduled on the same machine, which means if the machine goes down, it takes down multiple pods and the database may actually not be available. So the anti-affinity, so you'll be able to specify a rule to the Kubernetes scheduler, which says, don't put two of my pods on the same machine. And this means that when a node goes down, it does not take multiple pods down, and you are insulated from the failure of a physical machine. The other way to achieve data resilience is to do a multi-zone or a multi-region type of pod scheduling so that an entire zone or region failure does not affect you. Or sometimes this is also done to get data closer to the end users for low latency. There are a variety of different strategies. Kubernetes supports a multi-zone style deployment where the Kubernetes masters are in a single zone, but the slaves, which are like in our example, Yugabyte nodes, will be across zones and will be highly available. But if you lose the zone on which the Kubernetes master exists, you wouldn't be able to control the cluster. So then some managed Kubernetes services like GKE, Google's Kubernetes engine, offer regional deployments where both the Kubernetes masters and slaves are deployed across regions, but that's not common across multiple clouds. And there's a lot of discussion going on for federation in order to deal with multiple different Kubernetes clusters across regions. And this is a great place to join the community. Like, we're working with the community to make sure that, you know, the best features of Yugabyte comes out. In order to integrate stateful sets with apps, right? Let's look at a simple example of how a Kafka bus to figure out like what Kafka topics exist or so on and so forth. Now, there's different Zookeeper pods that need to talk to each other, and inside they can just refer to each other using the pod names, the ordinal numbers. Now, if you're within the same namespace, you can reference it using just the pod name and the namespace, and you don't need to give anything else. And if you're referencing it from an external cluster, you'll need to give the fully qualified name. And in this example, we're mostly using the fully qualified name because it's both readable and less error prone. Like, you keep hearing of all these examples where somebody dropped a production database by mistake, and all of those happen when there are environment variables that are not fully qualified. So we're just going with recommending fully qualified names. Okay, so let's talk about a couple of day two operations, right? So let's say you have your development has been built. Now you want to deploy in pre-production or production. What are some of the common things to think about? The first thing is, what happens if there are failures? That's like the number one ask. It often comes up even before, but it definitely comes up when you're going into pre-production/production. So a pod failure is automatically handled by Kubernetes. It will replace the pod with a new instance of the pod. And because of the fact that we're running in a stateful set, it has the same network. So the node failure has to be like manually handled. So if the pod have to handle that manually unless it is a managed service like a Google Cloud service, a G Cloud service, where you can automate, like, you know, the replacement of the node, or in AWS, you can use an auto scaling group, or you can use a variety of techniques to automate. Nevertheless, that is typically manually handled. And the failure of local storage is like typically handled by mounting it to a new Kubernetes volume, right? Okay, let's talk about the second piece. So we've now talked about failures. Let's talk about a scenario where you want to upgrade the software. The Kubernetes supports two native strategies to upgrade. It has a on-delete strategy, which means nothing will get upgraded until you delete the pod. So you apply the upgrade and delete the pods one by one manually. Where is this useful? If you take the example of an RDBMS like Postgres and you have master-slave replication, you want to be very careful as to when you do the upgrades to the master, because otherwise you'll get into the situation where do you want to promote the slave or not? And that's typically handled manually using the on-delete policy. But for highly available databases like Yugabyte, where a failure instantly re-elects a new leader in a matter of seconds and it starts serving, the rolling upgrade is a great strategy. What it means is effectively to your application, there is almost zero downtime. It rolls through the pods one after the other and upgrades the software, and you'll be able to retain your network identity and storage. So effectively, you'll be able to upgrade your entire software in the cluster without any downtime. Finally, a third very often asked question is, how do you do backups and restore? Now, you could think of backups and restore at the file system level, but that's typically not how databases work. Backups and restores are typically a database construct when you're dealing with database data in order to ensure consistency of the data. Yugabyte database can perform a distributed snapshot. So it takes a distributed snapshot and freezes the set of files as of the time you took the snapshot. And finally, it can copy them into a target and restore them back either into the same cluster or a different set of pods into a new cluster. And the number of nodes can change, the table names can change, the key spaces can change, so on and so forth. All right, the fifth point, and this is more of, and there, as you can see, in progressively increasing levels of like being complex and advanced. The fifth thing is, it's very easy to automate some of these operations that are done manually in a repeated fashion by extending Kubernetes itself using what are known as operators. So some of these operations, like for example, like auto-scaling a database when you have a lot of requests, right? It can be automated by the Kubernetes ecosystem, and it works the following way. It first observes what's going on in the current cluster. It then analyzes the data and then takes an action. So in our example of auto-scaling, it first observes what the CPU usage is across all the tablet servers in the cluster, and then analyzes this data to say, if the CPU usage has exceeded 80% for a minute and my max threshold for scaling out is not exceeded, then go ahead and act on it by adding another pod. And keep doing that in the loop, right? So it's pretty easy to automate such things. Another example is I want to take backups every day, nightly backups, or nightly snapshots with exports every other day, or so on and so forth. So there are a variety of places where something that's repetitive and manually done can be pushed into the system. And this works whether you're on-premise or on any of the public clouds, right? So it's a great way to get your database to become a platform. Okay, so we're going to take a real-world example. An e-commerce app called Yugastore. Yugastore is also on GitHub, and we're on top of a Yearn stack, which is Yugabyte, Express and Node.js as the REST API server, Yugabyte as the database, and React as the front-end language, the language for the UI. And all of this is deployed on top of Kubernetes. And you can see that, you can see the GitHub URL below, you can feel free to check it out. Okay, so high-level architecture. We've already looked at what is currently on the screen, the YB master and the YBT server, right, across different pods talking to each other. The YBT servers use the master's headless service in order to discover the masters and communicate, and the communication happens between them. In addition to having the headless service, we also have a load balancer for the UI, which redirects to the master UI port so that we are able to actually take a look at what's going on in the master. And this is the way to access it from the external world. Now, what we will do on top of this is add another deployment, and it's a deployment. It uses the deployment API because it's stateless. And we have Yugastore, which is the stateless app that communicates with the database. It does so by discovering the tablet service. So it goes and talks to the tablet servers and is able to individually, discover the pods inside. And Yugastore's UI is exposed to the end user with another load balancer service that the user is able to interact to, and that randomly, sends data to any of the pods underneath. Okay, so we're going to take a look at this in a demo fashion, right? So first thing I want to show is I'm going to show you the pods. What we see is there are 3 masters and 3 tablet servers, and they have their ordinal indexes, and they're deployed here. Now, we talked about a whole bunch of concerns, right? About performance, availability, so on and so forth. So I'm going to show you, I'm going to actually attach to one of the pods and show you some of these things. I'm going to attach to one of the tablet servers and show you the disks that they use. So what you see is it uses MNT disk 0 and MNT disk 1. And it actually uses the entire disk underneath. And this is running in Google Kubernetes Engine, GKE. And 350 gigs is the standard size of the disks that you can attach. And these are locally attached SSDs in order to give you a low latency, high performance kind of system. Okay, the second thing that I want to show is we talked about anti-affinity and surviving failures. So the second thing is, if you look at the actual IP addresses of the pods, the third number in the IP address represents the physical node on which these services are running. So what you see is that the masters are deployed on nodes 4, 5, and 6. These are the physical Google Cloud nodes. And the tablet servers, the 3 tablet servers, are deployed on 3, 4, and 6. And no 2 pods are scheduled on the same machine because we have the anti-affinity rule that's set. Okay, the second thing to see here is that there is actually another pod that has a whole bunch of random characters at the end to make it unique. This is one of the pods inside the app, which is a deployment. So, and we can see this quite easily by getting the deployment, which is Yugastore, and this is one of the pods inside that deployment. Now, with random characters attached to the end of these, they do not have a stable network ID, so they would not be able to talk to each other, as they should not, because these are stateless applications. The only way to reach these pods is through an external endpoint that we expose. So the next thing to look at is those endpoints. So if you look here, what we have as services, we have the YB masters and YBT servers, which are headless services because they have no cluster IP. And the reason for this is they simply enumerate the private IPs of everything inside. If you think about this in terms of a public cloud deployment, you don't want your database nodes to have public IPs. You want them to have private IPs, and you want to have some way to discover these nodes when a new application comes up. And the same pattern, design pattern, is being replicated by Kubernetes, except in a cloud agnostic way. Now, the YB master UI has an externally facing public IP. So you can go to this address to the port 7000 and we'll be able to see the master UI. And similarly, the app is exposed on this IP address with the port 3001, and we should be able to see it. So let's go look at each of these, right? So I've pulled up the same IP address on port 7000. And this is the master, the deployment. This shows you that there are 3 masters. They're deployed like in this configuration across the same cloud, region, and zone. But it's very easy to deploy Yugabyte across multiple clouds, multiple regions, multiple zones in order to make your system highly available and closer to the end user. The masters enter a raft election group where one of them becomes the leader. This deployment has a default replication factor of 3, and it has 3 nodes or pods, which are tablet servers. So we can go ahead and see the tablet servers. What we find is there are 3 tablet servers. This is their fully qualified name. There's tablet server 0, 0, 1, and 2, and they're all heartbeating to each other and alive at this point, and also deployed across the same cloud data center or region and zone. Okay, so let's go to the app. The app is on this tab. So as we said, it's on a different public IP and the port 3001. And this app is a simple bookstore app. It's what you would expect from a bookstore app. It's e-commerce, online visible, has a whole bunch of books inside it. And each of these books is categorized into a top level category. So there are business books, there's a whole bunch of them, and cookbooks, mystery and suspense books, sci-fi books, and so on. You can go into any of the books and get more details about the book itself. And these books are also grouped into some dynamic categories, like books with the highest rating or books with the most reviews, right? So based on the review count and so on and so forth. So there's a whole bunch of dynamic categories that they can be displayed by, grouped by. Now, one of the ways application developers love to do this is the static categories are really good in a SQL or a Cassandra-like system, which has the notion of tables. And the dynamic categories are really good for something like a Redis sorted set, which keeps the score and keeps them sorted by the score. And the score is highly variable. If more people give reviews, all of these ratings would change. Now, Yugabyte has a multi-model API. So it actually supports both a Redis API as a persistent scalable database and a Cassandra API as a persistent scalable database. It extends Redis to have the storage and the scalability, the built-in sharding, all of that. And it extends Cassandra to give it a document model with the JSON data type, with distributed transactions, secondary indexes, all with consistency. So let's actually try to connect to the database on this cluster. So notice that I'm connecting to T server 0 using the Cassandra shell, right? And so I'm in. So the first thing I can do is I can just say select some attributes of books, of course, from the yugastore.products table and just show me 3 of them, right? And so it just picks up 3. Now I can do the same thing where show me those books, but show me 3 books in the business category, right? And that's as easily done, and you see that the category is all business here, right? And you can do now, hey, that was great. Show me business books that are hardcover. I don't want to see paperback books. Yeah. So, and you can run those. So this is very, very similar to an SQL system and SQL-like query where you'll be able to model your pages, your static pages pretty easily based on these static categories. And categories like business and hardcover, they don't change very often. Now I'm going to connect to the same node instead and going to ask, show me across all the products that you have, show me the top 5 products based on sorted in a descending fashion by the number of reviews they have, right? And this is going to give me, and the with scores is actually going to give me the number of reviews as well, right? So, and this gives you the, and similarly, you can do the same thing by number of stars. Those are the 2 pages. The stars are like rating. So those are the 2 pages that we actually took a look at. All of this data is persistent. So on failures, it's highly available. And you can spread it low latency and so on and so forth. Okay, so we looked at like a whole bunch of things. So now, so what I'm going to do is I'm going to attach to the pod that's running like the stateless application, and I'm going to run a program that just goes and visits product pages at random. Okay, so with that going on, and if it were only that easy to make an application a hit, but is that even though I'm going through a single pod and you could have multiple pods here, like being like queried, what you see is that the number of read operations per second and write operations per second are distributed across the different nodes or pods inside the Yugabyte database. And you see that the number of tablets for the tables created are evenly split across the different pods. So this ensures that the total data is evenly spread, the total load is evenly spread, and writes, so on and so forth, right? So now let's do something. Let's go ahead and scale out one of the pods. So I'm actually going to open the YAML. So what you see here is I'm going to search for replicas. So the first thing you see is the master's replica. That's not something we're interested in. You see the tablet server's replica. This is something we looked at in the presentation. So I'm going to make that 4, which effectively means I want to change the number of tablet servers from 3 to 4. And then you just apply the changes. Okay, so what you will see is that instantly you see that a new tablet server springs up. What you will server that came up on a different node. So now we have tablet servers running on, that's a little too big. Okay, so we have tablet servers running on nodes 3, 4, 5, and 6, right? So there are 4 different nodes. The anti-affinity is kicking in. And what you'll see in the meanwhile, like while we've been talking, is that a new tablet server came up. The load starts instantly getting distributed across the different nodes. So the new node has already started taking reads and writes. And the different tablets are now slowly migrating from the old existing nodes into the new node. And this will continue in an online fashion until all of the nodes have an equal number of tablets. So it redistributes itself. And the data is copied in internally as compressed files, so it's extremely efficient. Right? So what you will see is over time, keep getting more and more tablets until we equalize across the board. Okay, so I'm going to stop that program and we can keep going forward. Okay, so a quick summary of what we talked about so far. The first thing is that there's already a lot of thought that has been put into stateful set, and they're getting increasingly more powerful. But nevertheless, as with any other system, ensuring high performance and data resilience requires careful planning, even if it is stateful sets. Day 2 operations are also getting simpler thanks to operator constructs. So it would be very easy to deploy your cluster and make sure that ensure that your intent is kept up to date, even in the face of a variety of different failures. But of course, like with any other automatic system, you would need to put checks and bounds to make sure that the system doesn't spiral out of control. And finally, there's a huge community here to help if you want to get started. Finally, wanted to say, whatever we demoed here, you can try this on your laptop. There are a variety of different failure scenarios that Yugabyte can handle, and all of those are documented on the website. You can go to the quick start to install Yugabyte on your machine. It only takes a few minutes, and you'll be able to try a variety of things like scaling out, linear scale out, follower reads, like data resilience and how it re-replicates data, and so on and so forth. All right, quick reminder. Join us. Don't forget to join us for our next online talk. Sid, our VP of Product, is going to be talking about how to scale transactional apps across multiple regions with low latency. So as you can see in the small diagram snippet there, that is an example of an app that's running across US West, US East, and Asia Pacific, Tokyo, but serving local reads to users with really, really low latency while keeping consistent writes. So please join us for that. And that's all I had, so we can open it up to questions.
Okay, Karthik, that was great. Thank you very much. So I want to introduce Sid Chowdhury, our VP of Products, who's joined us, and he's going to take some of the questions that came in during the online talk and discuss those with Karthik. Sid, over to you.
Thanks, Martin. Hello, everybody. Let's dive right in some very interesting questions here, Karthik. Let me start with the first one. If master and tablet server need a list of IP.
Yes, absolutely. So this is the whole purpose of a headless service. So when you create a headless service, the headless, it is Kubernetes. Kubernetes ensures that it's going to keep the headless, the CNAME updated with the list of IPs. So every time a new pod is added or a pod is removed, it's going to get updated, and that IP address is going to show up there. So auto discovery becomes really, really easy, but the applications have to be built with the knowledge that this IP can change. And traditional legacy applications would find it hard to do that. So that means you would still have to come in with a lot of operational expertise. But modern databases like Yugabyte, like we're having the advantage of building a database in this container era, which is really exciting. So we can take advantage of these type of constructs.
So when we do an add pod to the T server stateful set, the existing T servers in the stateful sets do understand the addition of the new node into that stateful set cluster, and the headless service is what exposes them to the outside world.
Absolutely. And on top of that, the clients that we support for Yugabyte, they're smart clients. So they also understand the addition of the node and will refresh their IPs and will be able to communicate with 4 nodes instead of 3 or so on and so forth.
Okay, great. This is a database question. You'll love this. How can Yugabyte handle blue-green deployments when it comes to database schemas and data models? For example, you can roll back app versions, but what if one of those versions had different data schemas that also need to be rolled back?
Yeah. So yeah, great question. So this is always tough in the land of databases. So first off, to make things easy, Yugabyte supports online schema changes. So you will be able to make your schema change, and it is the master's job, the Yugabyte master leader's job, to actually ensure that the entire cluster gets the schema change applied. Now, one of 2 things can happen, and this is where it requires some coordination with the app tier. If you are introducing a new column, right, then the assumption is you typically roll that into your schema first and then update your apps to reference the new column. But if you do it the other way, you're going to get app-facing errors because the new column doesn't exist until your schema has actually changed underneath. Conversely, if you are dropping a column, it goes the other way. You first change your app to not reference the column and then drop it in the database. But the entire thing can now be accomplished completely online because it's effectively, in some order, a change to the application tier and a change to the database tier.
Okay, great. So the next question, in the intro to Yugabyte DB slide, it seems like you are beating the CAP theorem by having both consistency and availability. What is actually the trade-off involved in picking Yugabyte DB?
Yeah, great question, guys. Great question. Keep them coming. So yes, it does seem that way. But if you look like beneath the hood, right, if you peer at it carefully, the CAP theorem only says you cannot get a perfect score for all the 3 things, like the C, A, and P, which is consistency, availability, and partition tolerance. But it does not say that you can get a perfect score for 2 and a high score for the 3rd. So that's what we do. Typical NoSQL databases chose to go AP, so 100% on availability, 100% on partition tolerance, but a high score on consistency, which means that, conversely put, some percentage of the time they will not be consistent. Yugabyte took the opposite direction because consistency is paramount to building mission-critical applications. So Yugabyte is a CP database, so it's 100% on consistency, 100% on partition tolerance, but it has high availability, which means in the face of failures, in a few seconds, we will be able to re-elect a new leader and will be able to service those few seconds. We will still be able to serve reads from a follower. We will not be able to take writes though, because if you open those few seconds of writes up, you open yourself to a whole can of worms with respect to inconsistency.
And I want to point out that increasingly this is the modern database design propounded by Google Cloud Spanner, even Microsoft Azure Cosmos DB functions in a single region in a very similar manner. Okay. Then another question. What is the unique selling point of Yugabyte DB over Cockroach DB?
Yeah, another often asked question actually. So Cockroach is it's a scalable but fully SQL compatible database. Yugabyte is a multi-model scalable database, right? So Cockroach DB offers things like joins today. Joins are in our roadmap, but Yugabyte DB is more optimized for low latency serving. So typically, if you do a deployment of Cockroach and you use SQL, it doesn't even matter if it's Cockroach or some other SQL database, you would use joins, you would normalize your data. But what that leads to in a scale-out system is as you continue to add nodes, your joins would get less performant if not written very, very carefully. Now, At Yugabyte, we went a different way. So the way you overcome this join problem is you do the join and then put the resultant data into a cache like Redis. And you have to figure out how to manually shard Redis, how to recover Redis on failure, and so on and so forth. So with Yugabyte, what we said is we're going to expose to the end user and make them carefully think about the choices needed to run in a scale-out system with efficiency. But you don't need a system like Redis. So very high performance, low latency system that you can practically serve out of. So you don't need to put this data into a different tier. Now that said, we do understand that joins are extremely useful as a tool for a lot of people, and we will have that in our roadmap. But we still believe that in order to serve, it is better to denormalize the data and pre-prepare it in the form you want to serve, and really think about how your access pattern comes about. Storage is cheap, but compute is expensive, so it's better to denormalize.
So, I can summarize it that today CockroachDB is SQL API with joins and high latency. Yugabyte DB is essentially a multiple NoSQL APIs with no joins but low latency.
Exactly.
There is a trade-off involved in making the choices.
Absolutely.
Okay. Last question. We run our databases today on virtual machines with attached storage. Good that Kubernetes is allowing local storage in containerized infrastructure. What kind of performance numbers do you see between the two approaches?
Yeah, wonderful. So we haven't compared apples to apples the Kubernetes performance versus VM performance. We are looking into that. We actually just started that effort. I've tried to run FIO on top of Kubernetes with local attached storage as well as our load tester. So the initial results are looking quite promising, but it's still something we have to do for an extended period of time under various failure scenarios and so on and so forth. So that is happening, but we do expect that it is fully possible to achieve pretty close to what a VM offers with local storage on a containerized ecosystem with the same local storage. We should be able to bridge the gap pretty well. At least I'm hopeful. So.
Okay, last question just came up. Are there plans to integrate a homomorphic encryption on the data center for requirements where data has to be encrypted so operations can be performed without having to decrypt the data and thus keep latency low?
In order to serve the data, so let's answer that in a twofold manner. And this often refers to encryption on the disk and not encryption on the wire. So let's focus on encryption on the disk. There are multiple strategies to do encryption on the disk. Like in a cloud provider, you can just ask the cloud provider to encrypt your data and not have control of the keys needed to decrypt the data. What that means is if you need to copy data out of the node, you pretty much cannot do it because you don't know the keys that were used to decrypt the data. So in that case, it's not an option. But let's say you do have control of the keys and have a key store, and it is possible to figure out what keys were used to encrypt the data, then yes, Yugabyte should be able to, effectively, Yugabyte is a strongly consistent database, which means without encryption, the way it works is internally, we copy the compressed data files into a new node, bring it up, and let it join the quorum. So in the new case, you can copy the encrypted data files, provided with the same encryption keys, and bring up the new node and let it join the quorum, and it would work exactly the same. So yes, in some scenarios, yes, and whoever asked great question, please feel free to talk to us. We'd love to work with you to make that a reality. So.
Right. I said last question, but that's not true.
No, please keep
More questions are coming in. Any plans to support MongoDB's API?
We get this pretty often. So our theory around MongoDB's API is we're supporting a JSON data type natively in an SQL-like language. So if you think about what MongoDB offers in a Cassandra-like system, once it has the JSON or a document native data type, it really offers the ability to have a partition column, which is a primary key, and another data column, which is a JSON data type. So effectively, but Cassandra offers you an additional column where you can sort based on attributes. So we believe that this approach is actually more flexible, and it's also inherently sharded and supports distributed transactions and secondary indexes globally across the table. So we will support all the Mongo access patterns, but we probably are not going to add the Mongo driver anytime in the near future. And yeah, variety of reasons, all the way from data modeling simplicity.
I think, there is also another way to look at it. With the combination of the Cassandra API looking more like SQL, and the SQL API also coming
with the JSON.
with full JSON support.
Yeah.
And then Redis having as a third API for more simple key value style applications. We believe we have the right coverage necessary to build application, right? And also with integrations with technologies such as Janus Graph for a graph layer, with integration with Illesandra for a full text search layer,
and Apache Spark,
and Spark for real-time fast analytics. We have the right coverage necessary for building such applications.
Absolutely, yeah.
Okay, one more question. What is your best tools to monitor the cluster when running in Kubernetes? Do you plan to integrate with a service mesh like Istio?
The Kubernetes integration story is in production is something we're still looking into. We have our own enterprise edition tool that we use, and that is something that we will offer. It comes with built-in metrics, monitoring, alerting, like ability to do distributed backups or place data in faraway data centers and get the system tuned appropriately, so on and so forth. Specifically with a service mesh, we haven't looked into it, but would love to hear about your use case and see how we can move that forward.
Yeah, I can add a little bit more to that. So each layer of the database exposes metrics in a Prometheus format, and Prometheus is the de facto standard. Essentially, the entire cloud native ecosystem is moving towards. So essentially, Yugabyte DB running on top of a Kubernetes cluster. Now you have the database full stack as well as Kubernetes own full stack, all exposing metrics at different ports in Prometheus format. All you have to do is pick a Prometheus server and let it point to all these different endpoints that you have, and then you have essentially built a performance monitoring solution that covers Kubernetes as well as Yugabyte DB. That's the most flexible, most, I would say, simple way of looking at, and then you build on top of that system for your own, if you want to build your own alerting and
you can use the alert manager.
Additional integrations. Okay, looks like we have covered all.
So as Sid mentioned a little earlier on, or maybe in Karthik, we will make an on-demand version of this available on the website within the next 24 hours. If you do have any additional questions, at yugabyte.com or directly to Sid at Yugabyte, and we'll be able to respond to those quickly. And one final reminder, upcoming on April 26th, we have another of these online talks, Scaling Transactional Apps Across Multiple Regions with Low Latency. We hope you can join us for that important and interesting topic. But for today, thank you very much for joining us. Goodbye.